Now moving forward, now we'll go on to the next part. Now the next part is the numerical, and a very important numerical. Almost every ISC every year question from here is set a simple numerical. I'll just give you one formula, but before that let us see what is the topic. So the topic is what is called density of the cell. Now if it is the density of the cell, so then density, okay, here we go. So density of the cell. Now when I say cell here I mean the unit cell. Now how do I calculate density? Now you know that density is equal to, in lower classes you have learned that density is equal to, so in this case if I am taking density as rho, is equal to mass by volume. But for a unit cell, now this mass and volume, and considering that our unit cell is cubical, so cubical means if the side of the cube is A, all the three sides are A, means volume is understood, so that volume is what is volume of a cube is what is A cube. Now when you are calculating the mass, mass is what is equal to Z into M or A, usually we call it as, okay, I'll take it as A, so that is Z into A divided by NA, where Z is standing for the rank of a unit cell. Now when I say rank, what is the total number of constituent particles present in a unit cell, where A is standing for the atomic mass of that particular unit cell. For example, if it is sodium, then we take that A as 23, and if it is carbon, we'll take it as 12, and this Na is standing for Avogadro's number. Alright, then if that is so, Z into A into Na is what is your mass. So density of a unit cell is equal to mass by volume, and if mass is this, and we have to divide that mass by volume, so into volume, and volume is what is A cube. So that is why the density formula now. So if I am writing the density formula here, density of the unit cell is equal to Z into A. Again I am repeating, Z means the rank of a unit cell, and we know that Z, what is Z for the three kind of unit cell which you have seen? Z is 1 if it is a simple cubic cell, that is if it is a primitive cell. Z value is equal to 2 if it is BCC, body centered cubic cell. So we have discussed already this in the previous class. So Z is what is 2 for BCC, for primitive it is 1, and for a face centered Z value is what is equal to 4. So if it is face centered, then Z value or the total number of constituent particles which are present there in a unit cell is what is 4. So there you go. Then again going back to the formula. So the formula for density of the unit cell is mu is what is equal to Z into A over Na, and don't forget this Z into A by Na, as I discussed just now, is the formula for calculating the mass of that particular unit cell, and then into volume, and volume, since it is cubical, so volume is what is A cube. Now in case if you have forgotten what this is, so this symbol here is standing for the density of unit cell, density of the unit cell. Then Z is standing for the rank, rank means the total number of particles present in that particular unit cell. A is standing for the atomic mass, so of that particular element, atomic mass. Then you have next one as Na, which is your Avogadro's number. So I hope you still remember what is Avogadro's number. So this is what is equal to 6.023 into 10 to the power 23. Yeah, don't get confused with this 3. It may be sometimes 6.022 into 10 to the power 23, and it is sometimes written 6 into 10 to the power 23 only. So it depends, like whatever is given, so that is what you will be taking, 6.022 or 6 into 10 to the power 22, whatever is given in the question, that is what you will take. Or if it is not given, then you can take it as 6.022 into 10 to the power 23 is what you can take. Then finally A cube, so that A is standing for the edge length. Edge length means, supposing if this is the unit cell, if this one is your unit cell cubical, this is what is A. Now why A cube then? Why we have A cube in the formula? We have A cube in the formula because volume of a cube is side cube. So that's why the volume, this A cube that you see there in the formula, is what is edge length. So edge length, and then edge length cube is what is going to give you the volume of the unit cell. Now you can see altogether how many terms are there in the formula. You have density 1, then here rank 2, then atomic mass 3, Avogadro's number 4, and volume 5. Now there are 5 terms, that is what you see there in the formula, and out of these 5 terms you will be given directly or indirectly 4 terms. Values will be given to you in the question, and you have to find the 5th one. For example, they will give you everything. They will give you Z, they will give you, Z they may not give you directly, but then in the question will be written BCC. Then you have to understand BCC means, BCC means Z value is 2. If they write that it is FCC, then Z value is what you have to take it as 4. And similarly, if it is primitive, then you have to take Z value as 1. Then A, depending upon what atom or which element it is, A value, atomic mass you have to write, Avogadro's number, then A's length will be given. Yes, also one more thing, A's length in most of the cases, it will be given in picometer. And when you are calculating density it may calculate in gram per centimeter cube. So you have to convert this picometer into centimeter. Do not forget to convert that picometer into centimeter. I hope you know the relationship between picometer and centimeter. So picometer must be converted into centimeter, or in some cases when density is given and then if you are asked to find the edge length, then that centimeter or centimeter cube which will be given there in density must be converted into picometer cube. Okay, we will see that as we solve the question. Now let us take a question. I'll solve maybe 2-3 different type of question. Okay, I'll start with the first one. Now listen to the question. An element whose atomic mass is 60. So okay, atomic mass is given. So at first only let me write atomic mass is given as 60. So the next one, having a face centered. Okay, so it is very clearly mentioned that it is face centered cubic cell. So face centered means the value of Z is known to us, and face centered has Z value as 4. So the second value is also given to you. Has a face centered cubic structure and has a density of, so I'll take again density also. There density is also given, and density is given as 6.23 gram per centimeter cube. This is what is the density which is given. And the question now is asking you, what is the edge length of the unit cell? What is the edge length? Again I am repeating, what is the edge length of the unit cell? Alright, now going by the formula, so here it is. So A you have, Z is there, rho is also there, and I should also tell you here Avogadro's number is not given. So as Avogadro's number is not given and then you are asked to find the edge length, so we will take Avogadro's number. So I'll take Avogadro's number as 6.02 or 02 into 10 to the power 23 is what I am going to take it as Avogadro's number. So that means I was telling you that out of the 5 things, 4 things will be given to you directly or indirectly. Now here you are. A is 60 atomic mass, Z is given as 2, then density is also given 3, and Avogadro's number is also more or less you will treat it as given because you know it. And finally the question is asking you, what is the edge length of the unit cell? Now if I am using the formula, now I was telling you before that density as you can see is given in gram per centimeter cube, but then edge length, and edge length is so small that it will not come in centimeter. Centimeter is too big a unit for edge length, so we must convert this density. So here it is, density 6.23 gram per centimeter cube. If I have to convert this into picometer, gram per picometer, 1 centimeter is equal to 10 to the power 10 picometer. So if that is so, then if I want to convert this gram per picometer cube, then I have to divide this by 10 to the power 10 into 10 to the power 10 into 10 to the power 10, which I will divide it as, and then write it as 10 to the power 30. So this is to convert, you can see that gram per centimeter cube is what I converted into picometer cube. So since I want my edge length, which is very small, in picometer, so that's why I converted this centimeter cube or per centimeter cube into picometer cube by dividing it by 10 to the power 30. Then using the formula which you have learned, density is equal to Z into A or M, whatever you like you can write, and divide by NA into A cube. Now let's write down the values, or if you want this A cube you can make this into a subject, you can interchange it. So A cube I am going to take it there. So A cube is equal to Z into A over Avogadro's number into density. Now by putting the values now, the A cube is equal to Z, so FCC, so I'll write that one as 4. Then A is given as 60, so let me write that as 60. Then I'll divide this by 6.02 into 10 to the power 23. This is what is your Avogadro's number, and into density, and density is given as a 6.23 divide by 10 to the power 30. So instead of writing this divide by 10 to the power 30, so let me take that up and write down. I'll write this as 10 to the power 30 there on the top. So actually 6.23 is divided by 10 to the power 30, and that much gram per picometer cube. So but then I'm going to take that 10 to the power 30 up and then write down. So in that case now your A cube will come. Okay, by the way, I'm going there now. So A cube, if you use a calculator, let me use a calculator. So if you use the calculator, okay, then this value is going to come here as 64 into 10 to the power 6 picometer cube. So this is what is A cube. A cube is standing for the volume, but the question is asking you to find not the volume, rather the question is telling you to find the edge length. Edge length means if A cube is this, then we have to find A, and A means you have to find the cube root of, on the other side, cube root of 64 into 10 to the power 6. So A is equal to 64, cube root is 4, and 10 to the power 6 is what is 10 to the power 2 or 100. So A is equal to 400 picometer. So there you are. The edge length of that particular unit cell is what is 400 picometer. Yeah, this is what is the first type of question where you are asked to find what is the edge length. Again, I am repeating, some other cases edge length will be given to you and you may be asked to find density, or as I said, out of those 5 things, 4 things will be directly or indirectly given to you and you have to find the fifth one. Okay, now let us see a little different kind now. The second type of question is the unit cell of an element of atomic mass 96 and density 10.3 gram per centimeter cube is a cube with edge length of 314 picometer. So now you can see edge length is given, A is given, density is also given. Find the structure of the crystal lattice. So find the structure means you have to find whether it is BCC, whether it is a simple cubic, or it is FCC. That means you have to find here indirectly the question is telling you to find what is Z. So again I should tell you that now after calculation of Z, if Z value is coming 1, then you will say, since the question is find the structure. Structure means if Z value is 1, then you will say it is simple cubic. So you have to write that. Then if your Z value is coming 2, then you have to say the crystal is BCC or body centered cubic cell. And if Z value is coming 4, then you have to say it is FCC. So the question is asking you to actually to find what is the value of Z, but indirectly they have asked what is the crystal lattice, what is the structure of a crystal lattice. Okay, I'll read the question again and then write down data which are given. The unit cell of an element of atomic mass, okay, atomic mass is given, so let me write atomic mass is given as 96. Density is given, so density is given as 10.3 gram per centimeter cube. So that is what is 10.3 gram per centimeter cube. Then in a cube with edge length, okay, edge length is also given, so let me write edge length is given as 314 picometer. So there, and then again Avogadro's number is not given, so you know what is Avogadro's number. So now the question is telling you what is the structure or what is Z. So again going by that formula, so density is equal to Z into A or M divided by NA into A cube, and the question is to find Z. So if I directly make Z the subject, then Z will be equal to density into Avogadro's number into A cube over A. I think this is what is going to give us the value of. Now let us write down, some modification is required. Now first modification that is required is either you convert A into centimeter that your A, which is your edge length, which is given in picometer, you convert it into centimeter because the density is given in centimeter. So let's do that. It will be, or you convert this into picometer. So it's your wish whether you convert density into picometer or you convert the edge length into centimeter. So I think it will be easy if I convert it into centimeter. A is 314 picometer, and you know that 1 centimeter equal to 10 to the power 10 picometer. So if I want to convert this picometer into centimeter, then this is what I'll be multiplying with 10 to the power minus 10. So yeah, when a picometer is divided by 10 to the power 10 zeros, then I'm going to convert this into centimeter. Alright, now let me write the values now. Z equal to density. So density is 10.3 into Avogadro's number. I'll take it as 6.022 into 10 to the power 23. And A cube. Just now we found out what is A. A is 314 into 10 to the power minus 10 is what is A. But I want A cube. So if this is A, then A cube will be this. And this whole thing is what I'll divide by A. And A is given as 96. Now if you use your calculator, then okay, let's see how much it's come. Oh yeah, it is coming very almost equal to 2. So Z value is coming 2. Now since we have already discussed, if Z value is 1, then it is simple cubic there on the top. So there. So if Z value is 1, then it is simple cubic, and if Z value is 2, then it is BCC, and if Z value is 4, then it is FCC. And since we got our Z value as 2, so then we can now say what is the structure. So we can say our structure is body centered cubic cell. So since the question was asking you what is the structure of this lattice, then you can say the structure of this lattice is BCC. Yeah, such type of question, a very simple base question is always asked. Now instead of saying what is the structure, sometimes they'll say what is the nature of the cubic unit cell. Again I should tell you what is the nature means. Again you have to find the same Z value is what you have to find, and your Z value must come either 1 or a 2 or a 4. Now nothing other than this. If it is coming 1.99, don't forget that you have to take it as 2. 1.9, maybe 2.04 or maybe 4.1. Don't expect exact number 4. You may get very close to 4. It's all because of the values of Avogadro's number that we take. So you can round it off to the nearest, and don't write the answer, final answer in decimal. It may come in decimal, but you'll round it off to the nearest number, and that will be either 1 or a 2 or a 4. Okay, so that is how you solve a question based on this one. Now let's see now the third type of question, even though it's nothing different from what you have done already, but slightly different it is. Okay, now listen to the question. It is saying Kf means potassium fluoride has NaCl structure. Okay, now I should tell you that we are yet to do that structure of NaCl. So the sodium chloride structure is FCC. So indirectly here in the question they are saying Kf has NaCl structure. Since NaCl is there in a syllabus, do a detailed study of NaCl. So then since we know, you don't know because I have not yet reached there. So since we know that NaCl has FCC structure, so then we will consider that Kf also has FCC. That means FCC structure means Z value is what I have to take it as 4. So see there, indirectly you are given here the value of Z. So then Kf has NaCl structure. What is the distance between potassium ion? Okay, so what is the distance between potassium ion and fluoride ion in Kf? If the density of Kf is 2.48 gram per centimeter cube. Now let me write down things which are given to us. So indirectly you are given Z. So since it is written your Kf is NaCl structure means, and since NaCl structure is FCC, so Z value is 4. Next they have given density. So density is given as 2.48 gram per centimeter cube. But now since the question is asking you what is the distance, so distance is very small, so I have to calculate it in picometer, but here density as you can see is given in centimeter cube. So what I'll do, I have to convert this into picometer, so I will multiply this with 10 to the power minus 30. In fact, I am dividing this with 10 to the power, this I am dividing by 10 to the power 30. So if I take it up, it becomes 10 to the power minus 30. So density, now we can write, is equal to 2.48 into 10 to the power minus 30 gram per picometer cube. Now we have converted the centimeter cube into picometer cube. Then what is the molecular mass? So just below the question is given that potassium has an atomic mass of 39 and fluoride has atomic mass of 19. This will be given to you, you don't need to worry. So to find out what is A, or atomic mass, or in fact in this case actually it is molecular mass, so A is equal to Kf. Kf means potassium is 39 and your fluoride is 19. So the total of which is coming 58. So one by one, now see, I am calculating. I found out what is Z, I found out what is the density in picometer cube, and I also found out A. So three things. One more I need, and then I can move on to find okay. So 1, 2, 3. Oh, Avogadro's number, yes. Avogadro's number is something which you know already. 6.022 into 10 to the power 23 is what is Avogadro's number. And now the question is telling you, find what is the distance between potassium ion and fluoride ion. Now you will see this is slightly different from usual pattern, but then for this question also you have to find what is A. As you can see, A cube is missing, so we will calculate what is A cube. Okay, directly writing the formula of A cube. So by the way, same formula, but I am making A cube the subject. Then it is Z into M, or A divide, in this case actually it should be M because it is a molecule, density into Avogadro's number. If I write down here, then A cube value will be equal to 4 into 58 divided by your density was 2.48 into 10 to the power minus 30 picometer cube, gram per picometer cube, and Avogadro's number is 6.022 into 10 to the power 23. So then I think after calculation of A cube, then okay, let's multiply it. Then I need A. A means I need to find the cube root of this, and if you find the cube root of this, I think it will come 538. Alright, now if this is 538 picometer, the question is asking you what is the distance between potassium ion and fluoride ion. Now to find this one, you know, if this is the edge length, if supposing this is the unit cell, now if these are potassium ion, if this is potassium ion at the edge, so if you are asked to find edge length A, then that is what is your 538 picometer. But the question is asking what is the distance between potassium ion and fluoride ion, and in NaCl structure, you know, if cations are present there at the corner, then your anion fluoride is present somewhere in the middle here like this. So that means if I want to find what is the distance between potassium, what is the distance between potassium to fluoride, then this distance is what you have to calculate. And if you look at the diagram, this distance is exactly half of what is the distance from potassium to potassium, or what is the distance of the edge length. So that is why if I want to find the distance between potassium ion and fluoride ion, and that is what is equal to 538 divided by 2, and this is what is going to give you 269 picometer. Here it is. Yeah, practice a lot of questions like this. So you know, out of those 5 things, 4 things will be directly indirectly given to you in 5th one. Yes, if you see the board question, even if you see 2020, 2019, all questions, every year's question, there had been hardly any year where this type of question has not come in your board exam. So be sure, so take out some questions and try solving. I think you can surf the net for questions, or if you want, then I may give you some questions for you to practice. Yeah, this is what is your numerical based on. And yes, don't forget, we have also discussed some other derivations, but then the most important part related with numerical from this chapter is this. And yes, consistently question like this are coming there in the board exam.
Imperfections in solids. Crystalline solid state is characterized by a three-dimensional periodic arrangement of atoms or ions or molecules in space. Ideally, there should be a perfect order in this arrangement. However, crystals in nature are not perfect. They do not possess perfectly ordered arrangement. This is due to the presence of few impurities or due to dislocation of few of constituent particles from their normal positions. Any deviation from the perfectly ordered arrangement of atoms or ions or molecules in crystal is called imperfection or defect. Defects can be classified into two types: point defects, line defects. Point defects. Point defect can be defined as the irregularities or deviations from ideal arrangement around a point or an atom in a crystal. Line defects. Line defects are defined as irregularities or deviations from ideal arrangement in entire row of lattice points. In this chapter, we will learn only about point defects. The point defects can be further classified into stoichiometric defects, non-stoichiometric defects, impurity defects. Stoichiometric defects. If imperfections in a crystal are such that the ratio between the cations and anions remains the same as represented by molecular formula, the defect is called stoichiometric defect. These defects are also called thermodynamic defect or intrinsic defect. The stoichiometric defects are of two types: vacancy defect, interstitial defect. Vacancy defect. In a crystalline solid, some of the lattice sites are vacant. The crystal is said to have vacancy defect. This generally arises due to the absorption of heat from the surroundings, which results in the decrease in the density of the substance. Interstitial defect. Interstitial defect is caused when some of the constituent particles, can be atoms, molecules or ions, are present in the vacant spaces in the crystal structure. These vacant spaces are known as interstitial sites, and the particles present in these vacancies are known as interstitials. As the number of particles within the crystal increases, the density of a substance increases. Both vacancy defect and interstitial defects are generally shown by non-ionic solids. Ionic solids do not show these simple vacancy defect and interstitial defects. Instead, they show SCHOTTKY and FRENKEL defects. SCHOTTKY defects. SCHOTTKY defect is similar to vacancy defects. This type of defect is created when equal number of positive ion and negative ions are missing from their lattice sites, so that electrical neutrality is maintained. Here, mass decreases while volume remains the same. Presence of a large number of SCHOTTKY defect site lowers the density of the solid. Types of compounds exhibiting SCHOTTKY defects. SCHOTTKY defect is shown by highly ionic compounds which have high coordination number and small difference in the cations and anions. A few examples of ionic compounds exhibiting SCHOTTKY defect are NaCl, KCl, KBr, AgBr, and CSCl. Schottky defects maintain the electrical neutrality of the crystal. In sodium chloride, there are about 10 raised to 22 ions in 1 cubic centimeter of sodium chloride, and there are approximately 10 raised to 6 Schottky pairs per cubic centimeter at room temperature. Therefore, in sodium chloride at room temperature, there is 1 Schottky defect per 10 raised to 16 ions. Frenkel defect. If in an ionic solid, a smaller ion, generally cations, goes missing from their lattice site and occupies the interstitial site such that electrical neutrality as well as the stoichiometry of the compound are maintained, this type of dislocation is called Frenkel defect and also called as dislocation defect. This defect is a combination of vacancy defect and interstitial defect. It is a vacancy defect at its original site and an interstitial defect at its new location. Since no ions are missing from the crystal as a whole, Frenkel defects do not affect the density. Frenkel defects are common in ionic compounds which have low coordination number and large difference in size between cations and anions. Frenkel defects are found in silver halides due to the small size of silver ion and in zinc sulfide due to small size of zinc ion. In pure alkali halides, Frenkel defects are not observed because the ions are bigger than the voids. Impurity defects. So far, we have discussed point defects where there are no foreign atoms. Foreign atoms can occupy interstitial sites or lattice sites in a crystal. Defects in the ionic solids may be introduced by adding impurity ions. If the impurity ions are in a different valence state from that of the host ions, vacancies are created. Let us understand with the help of an example. Consider the crystallization of molten sodium chloride in presence of small amount of strontium chloride, SrCl2. During crystallization process, some of the sodium ions are replaced by strontium ions, Sr plus 2. For every Sr2 plus ion, 2 Na plus ions are removed to maintain electrical neutrality and also creates a cationic vacancy. Similar type of defect and behavior is observed when CdCl2 is added to AgCl. Non-stoichiometric defects. The ratio of combining elements in the compound is different from that required by the stoichiometric formulae. The defects which disturb the stoichiometry of the compound are called non-stoichiometric compounds. These defects are either due to the presence of excess metal ions or excess non-metal ions. Non-stoichiometric compounds are of two types: metal excess defect, metal deficiency defect. Metal excess defect. The solids with metal excess defect contain metal ions in excess to the stoichiometric ratio. Such defect is caused due to anionic vacancies, excess of extra cations at the interstitial site. Metal excess defects due to anion vacancies. In anionic solid, an anion may be missing from its lattice site, leaving a hole which is occupied by an electron, to maintain the electrical neutrality. The anionic site occupied by an unpaired electron is called F centers, where F stands for Farbencenter, which is a German word for color center. F centers are responsible for the color of the compound. This kind of defect is shown as alkali halides, such as sodium chloride and potassium chloride. Metal excess defect due to the presence of extra cations at interstitial sites. In this type of defect, metal excess is caused by an extra cation occupying the interstitial site. To maintain electrical neutrality, an extra electron is also present in some other interstitial site. This defect is found in crystals having Frenkel defects. Example: zinc oxide is white or colorless solid at room temperature. But when zinc oxide is heated, it loses oxygen and turns yellow color. ZNO gives Zn2 plus 1/2 O2 plus 2E minus on heating. The excess Zn plus 2 ion gets trapped into the interstitial sites and the released electrons get trapped in its neighboring interstitial sites and maintain the electrical neutrality. Crystals with either of these metal excess defects contain some free electrons, hence such materials are semiconductors. Metal deficiency defect. This kind of metal deficiency defect is created when a metal ion goes missing from its original lattice site. To maintain the charge neutrality, same metal ion having higher positive charge is added to occupy the vacancies created in the crystal. As this metal ion has higher positive charge, it will occupy only some of the sites to balance the overall charge, and other sites will be left vacant. Example: FeO is mainly found having a composition of Fe 0.950. In crystal of FeO, if some of the Fe2 plus ions goes missing, then the loss is compensated by the addition of Fe3 plus ions. In this way, though the overall charge is balanced, some spaces will be left vacant in the crystal.